The Module 3 Honors Test Review. So we started with this proof, and I did copy everything into my notebook. And you can see that we were given two congruency statements. I'll mark them on the picture if I'm able, and I'm trying to prove in the end that side LJ is congruent to side NJ. But this is all we know for starters. So they tell us that LK is congruent to NM, I can mark that, and that KJ, so from here to here, is congruent to MG. I'm able to mark that. So I mean, common sense already tells us that if these little pieces are equal and the bigger pieces are equal, then of course the whole thing's going to be equal. And what should already be popping into your mind is part plus part equals the whole. But let's just get this down formally in the proof. How did I know that? Why was I able to mark those things? Well, that's what was given to us to start this proof. Now, the next reason is definition of congruent segments, or definition of congruent. What does it mean to be congruent? It means that the same shapes are going to also be the same size. They'll be equal in measure. So we're able to drop these congruency markings, and we can just say that the distance between L and K is equal to the distance between N and M. And same thing with the second statement. We can just drop those congruency statements. Oops, I almost put the symbol over the top. That's gone now, okay? So now notice that these don't have markings over the top of them, so this is gonna enable us to ease down here into the proof a little more. That's definition of congruence. So where is this coming from? This step, I wish they'd taken an extra step. This is a little difficult to see. I'm gonna grab a highlighter. And what you should notice is that in this equation right here, I was told that LK was equal to NM. Well, I still have LK on the left, and I still have NM on the right. What changed really is that KJ was added on the left and MJ was added on the right. What did we know about those? We knew those were equal to each other, so we added something of equivalent value to each side of this equation. That's the addition property of equality, that says that as long as you add it to one side of an equation, you'll need to do it to the other in order to keep things balanced and equal. Okay, now we need to use the segment addition postulate. It's going to be the reason for what I write right here. So let me start with this segment, and I do have a reason for what I'm about to do. I want it to match what we've already written in the proof. But you can see that these are the two pieces. We've got this distance between K and L and J and K, and together they're gonna add up to this whole entire segment. I could start with either part. I'm gonna start with the small part. I could call this KL or LK, it doesn't matter. But notice we had written LK over here. So I'm gonna go ahead and say LK. So the small piece plus the next piece, which is KJ, that equals that whole entire side, LJ. That's what segment addition says. The part plus the part equals the whole. I'm gonna do it again here because there's no opportunity to do it later. So let's write it now. So over here, same thing. I'm gonna start with the little piece NM plus MJ. The piece plus the piece equals the whole thing, which is NJ. I was able to write both of those equations because of segment addition. So where is this coming from now? Now we're taking statement 3 and rewriting it when we write statement 5. Notice that we had LK plus KJ on the left. And what does LK plus KJ equal? So this is going to be replaced with its equal value there, the left side of the equation. And then the right side of the equation was Mn plus Mj. and nm plus mj is the same thing as nj, so that ends up down here. We replace that as well. So we use substitution. We replaced both of these statements in 3 with their equal values from line 4. And then the only thing that's changing going from line 5 to line 6 is where we're adding back in the congruency markings. What does it mean to be congruent? If 2 points are the same distance apart, then the segments that form them are the same shape. Remember, definition of congruence works the same forwards and backward. So definition, we can just say definition of congruence. It is specifically congruent segments. So that's what that proof looks like. All right, let's try the proof in number 2. So this was an if-then statement on your paper. If segment AB was congruent to segment CD, then X is equal to 7. The hypothesis is what we know, and we're trying to conclude this beyond a shadow of a doubt. So that's where the given and the proof statements came from. And then these pictures were given to you in the proof. All right, so this much is set up. Notice that I'm going to want to prove that X is equal to 7. I'm not going to want to have a congruent marking. I'm going to want to have an equal sign. So let's go ahead and drop that right now. I know that since those segments are congruent, the distance between A and B is the same as it is from CD. And the reason is like what we saw up above. That's definition of congruence. And now I can see that segment AB, there's an expression for the distance between those points. Let's replace AB with that expression. So 4x minus 6. Same thing with CD. I know exactly how far apart they are. They're 22 apart. So we replaced these two things with their equivalent values. That was substitution. And now let's just go ahead and solve. So it's a minus 6, so I need to add 6 to both sides. It'll cancel out on the left, and we'll have 28 there. What did we do? We used the addition property of equality. And then divide both sides by 4, and we end up with x equals 7. Remember, I know I'm done because that's what it was we were trying to prove. X equals 7. And what did I do going from line 4 to line 5? I divided. So I used the division property of equality, just repeating what I did up above. Okay, and number 3, we have this long statement, and we do need to rewrite it and decide the truth value. So it is true. If you can divide a number by 4, it's definitely going to be even, and we'll be able to divide it by 2. So what about the converse? The converse is formed by switching the hypothesis and the conclusion. So the conclusion was it's divisible by 2. If a number is divisible by 2, then the hypothesis goes to the back, then it is divisible by 4. So if we switch that around, is that still a true statement? Well, we have to say that's false. And since it's false, we need to give a counterexample. So a good counterexample would be, for instance, the number 10. 10 satisfies the hypothesis. It is divisible by 2, but it is not divisible by 4. And if we can find even one exception, then remember we have to say it's false. Okay? All right, what about the inverse? We'll always go back to the original statement. The inverse is formed by negating and negating as it sits. So if a number is the opposite of divisible by 4, is not divisible by 4, then it is not divisible by 2. Remember, if there was any doubt as to the truth value, the converse and the inverse always have the same truth value. So if we were correct up here, this one must be false. So let's come up with a counterexample. Come up with a number that is not divisible by 4. Okay, I'll go with 6. 6 is not divisible by 4. But it's not true that it's not divisible by 2. It is divisible by 2. So it satisfies this condition, but not that one. False. And then the contrapositive, back to the original, negate and flipped. So if a number is not divisible by 2, then it is not divisible by 4. The original statement was true. I know that the contrapositive must be true as well. If a number is not divisible by 2, then it's not even. The multiples of 4, we've got 4, 8, 12, 16, 20, and so on. Every single one of those is even, and they're all divisible by 2. So if it's not divisible by 2, it would have to be an odd number, and you won't end up with a multiple of 4, okay? All right, moving on. We have to name the property illustrated by each statement on numbers 4 through 11. So number 4, what changed from the hypothesis to the conclusion? This 10 disappeared. We actually subtracted 10 from both sides. So this is the subtraction, I'm going to abbreviate, property of equality, okay, subtraction property. What changed in number 5? X is no longer over 3. That's being divided by 3. If I multiply by 3 and times 3, these will cancel out and we'll end up with negative 45 on the right side. So that's the multiplication property of equality. Okay. What's changing from the conclusion, from the hypothesis to the conclusion? Instead of 4x minus 5, it's just 4x. So we had to add 5, and sure enough, adding 5 over here would give us 17. So the addition property of equality. What changed is the fraction went away, and to get rid of 1/5, we could multiply both sides by the reciprocal, 5 over 1, and those would cancel out. So this was the same as 5. Okay, and number 8, the parentheses are gone, and the 5 was being multiplied through a sum. So 5 times x and 5 times 7. And notice the right side didn't change, but we just used the distributive. Oh, that should have been, yeah, that's correct, sorry, on the left-hand side. So this is the distributive property. Okay, the measure of angle 1 is equal to 25, and the measure of 2 is equal to 25. So what they've really done, you could say transitive, but they've taken this statement and written it over here, and now it says the measure of angle 1 is equal to, instead of 25, we've replaced the 25 with the measure of 2. Probably substitution works best here, mainly because if you look in the middle of this problem, those aren't identical to each other like we're about to see down here. In this next statement, AB equals BC, and right away that same BC equals CD. So notice this is literally in the middle, and what do? We're going to skip from the first to the last and jump over the thing in the middle to say that AB equals CD. And anytime you cut out the middleman, that is the transitive property. And then we've already seen this one, but multiplying the 3 through would cause that 3 to cancel out of the denominator and just leave us with 3x minus 2. That, once again, is the distributive property. All right, in number 12, we just want to take this sentence, 16-year-olds are eligible to drive, and write it in if-then form. Well, what's the hypothesis? What comes first and then the other will follow? Well, according to this, being 16. If you're 16, you are then, of course there's more you have to do to drive, but you are, in the state of Florida, eligible to drive. So if a person is 16 years old, then they are eligible to drive. Or if they are a 16-year-old. And that's all we had to do was write that in if-then form. Sorry, you could not see that. Okay, the remaining 4 give a counterexample if they're false. So if you take a number and square it and you get 16, will that number always be 4? And I'm gonna have to say that that first one is false. And here's my counterexample. Oops, I wrote that backwards. If you square -4, -4 times -4 also equals 16. So x could be -4. That's why it's false. Number 14, if you live in Charlotte, then you live in North Carolina. Well, there certainly is a Charlotte in North Carolina, but it turns out there are other states that have Charlottes in them. I looked it up. There's a Charlotte in Maine, there's a Charlotte in Texas, etc. So that's false. And I'll just say other states have towns named Charlotte. If tomorrow is Friday, then today is Thursday. Well, the only time that we could say, tomorrow is Friday is if indeed it were Thursday. So that one is true. And then if an animal is spotted, then it is a Dalmatian. And we're going to have to say that is false, because just like we could think of some Charlottes that weren't in North Carolina, we could make this statement true without X being 4. The same thing. I can make an animal spotted, but it doesn't have to be a Dalmatian. This is false. I'm sure some come to mind. I'll just say, for instance, a cheetah. A cheetah is spotted, but it's not a Dalmatian. It's not a dog. Okay, so we came up with some counterexamples. All right, looking at the figure here, a plane parallel to ZYX. Well, ZYX is essentially the top of this box that we're looking at. So the flat surface that's going to run parallel to that will be the bottom of the box. The bottom of the box is down here. And we just wanted that. I have 4 corners to choose from. I'm naming a plane. I just need to use 3. You can pick any 3 you want. Since they chose Z, W, and X, I'll just choose the matching ones down here, T, U, and V. So plane T, U, V. As long as you're naming the bottom, you're good to go. A segment that is skew to TS that contains point W. So skew means it's not going to intersect TS. It does not touch TS, but it's also not parallel. So TS runs like such. There are lots of extra other segments here that are not parallel. There are 2 that contain W that we could use. Either WZ, that will never touch TS and it's not parallel to it, or WU back there, that works. WX actually does run parallel, the top and bottom of the box. So I would say either Z, W, or WU. Name all segments that are parallel to SV. So SV is here. Any other segment that's running in that same direction are those 4. The same long edges of the box. So we have SV, we have YX, ZW, and at the bottom back there, TU. Those all run parallel to one another. All right, finding the measures of the numbered angles. So I do have these drawn, so we'll just use this paper for that, and I'll just add in the expressions as we go. So 9 is 2x minus 4, and 10 is 2x plus 4. Notice there's a little review in this part. There's a review in our review, but those just make a linear pair. So if I add them together, the measure of angle 9 plus the measure of angle 10 has to equal 180. I can substitute in those expressions and solve. The 4's are going to cancel out, so we just have 4x equals 180. Divide both sides by 4, and x is equal to 45. Okay, the same thing is actually true here with 11 and 12. They lie along that line and make that linear pair. So the measure of angle 11 plus the measure of angle 12 equals 180. The measure of 11 is 4x, and 12 is 2x minus 6. So 4x plus 2x minus 6 equals 180. 6x minus 6 equals 180. Add 6. 6x is equal to 186. Divide both sides by 6, and we end up with 31 for x. 22, I'm really sorry, is the same exact thing. They make a linear pair. So the measure of angle 19 plus the measure of angle 20 equals 180. 19 is 100 plus 20x, and 20 is 20x, and that's equal to 180. So 100 plus, group up these terms, 40x equals 180. Subtract 100 from both sides, and 40x equals 80. Divide both sides by 40, and x is equal to 2. And then we finally move on to the ones where they are running parallel to one another. So these lines are parallel, and I can see that x and y, these are alternate interior angles, and those types of angles are congruent to each other when formed by parallel lines. X, however, is making a linear pair with 55. So if I subtract 55 from 180, that's going to leave me with 125. And then these are going to be congruent to one another, so they have the same measure. X is equal to y, and they both equal 125 degrees. All right, number 24, our lines are parallel. Those are the interior angles, so these are both outside the lines on opposite sides. These are alternate exterior angles, and alternate exterior angles are congruent. So this has the same measure as that. So we'll set 104 equal to x minus 10. Add 10 to both sides, 114 is equal to x. And number 25, these angles are inside the parallel lines. The lines are parallel on opposite sides of the transversal. We have another pair of alternate interior angles, and we saw earlier those are congruent. So 2x minus 15 is equal to x plus 55. Let's get the x's together by subtracting x. So x minus 15 equals 55, and then add 15 to both sides, and you end up with x is equal to 70. All right, finally, we do have parallel lines again. We have both an x and a y, and this is the only angle I know. 105 is down in this lower left position, and so is this one. They're sitting in the same spot with respect to that intersection point. These angles are corresponding. They're in the same position, and corresponding angles are congruent when formed by parallel lines. So 3x minus 15 equals 105. Add 15 to both sides, and we're going to get that 3x is equal to 120. Divide both sides by 3, and x is equal to 40. And then we can plug 40 in here. 3 times 40 is well, we know that, I'm sorry, I don't have to do that. I know that this angle is 105 degrees, right? It corresponds. So that 105 degree angle is going to make a linear pair with this one. So this is 105, 105 plus y plus 25 is equal to 180 degrees. Group up my like terms. I'm going to get 130 plus y equals 180, just adding those together, and then subtract that, and we get that y is 50.